All right. Okay. All right. So, lecture 4. We are rocking and rolling with support reactions. I think today is the perfect day to sort of describe the overall logistics for the day-to-day lectures, because this is a perfect example. So, homework number 1, you turned that in on Friday. That has been graded, and the solution is posted, okay? If you go into Blackboard, there's a folder, and it's called something like Older Homeworks and Solutions, and so you'll see the homework assignment and the solution under it. And in terms of performance, everybody did very well. If there was any mistake that happened, it was honestly just using like a pin support when it was really a fixed support, or a fixed support instead of a pin support, etc. Like, if that was your structure, then the problem was done correctly. It was just transcribing from the book to the paper. That was the only error. So it seems like everybody understands the concepts. It was just making sure you pay attention to the boundary conditions. So, you turned the homework in on Friday. It was graded over the weekend, so the solution is posted, so you have that solution. Then there's a homework that's due today, okay? So you all should have already turned that in. And the idea is that that'll get graded between now and Wednesday, and then that solution will be posted, and then the homework that's assigned today is due Wednesday, and then we'll just keep on going with that pattern. So you're in a pattern of doing homework regularly, and we're in a pattern of grading homework regularly. So we'll try and keep up with that. The homework was pretty straightforward to grade, and that's one of the nice things about the homeworks being pretty short, is that grading them usually goes pretty quickly because it's not a lot of work. Okay, any questions? All right, let's continue on with our discussion of reactions. I think we have 4 lectures on reactions, so let's just sort of recap what we did last time. So last time we was sort of the shake the rust off lecture, if you will, on statics, but we also tried to make sure that what we were doing was couched in a little bit of reality. I mean, this is a core civil engineering class, and so I want to make sure that everything that we're doing is sort of couched, whatnot, in reality. So what we're doing here is just summarizing what we did last time. So we've got our 3 boundary conditions that we've explored. We haven't dealt with this one yet. That's going to be a Wednesday topic, because on Wednesday I want to focus on concentrated moments. That's what I want to focus on. And so that's not only just concentrated moments as loads, but also as reactions. So what we primarily focused on were hinge and roller, or pinned and roller boundary conditions, and we focused on concentrated loads and distributed loads. And really the big point is that that distributed loads can sort of be turned into concentrated loads, so that you're not really handling them any differently. You're just using the magnitude of that load as sort of the area of the load, if you will, and just placing that concentrated equivalent force wherever the centroid is. So hopefully that concept was pretty straightforward. Now what I'm going to do today is I'm going to take those loads and I'm going to incline them a bit. The main reason for doing this is really to just sort of get your trigonometric muscles firing again. We are going to need to explore trig in a wide variety of fashions. I always want to make sure that I'm couching what we're talking about in an area of reality. And so if I'm being honest, and this is the bridge engineer coming in me, I'm not really sure that I've had too many bridges that have had vertical incline loads. Most of the vertical loads that get applied on bridges are a function of just gravity. They're just up and down. But that doesn't mean that we as civil engineers don't need to deal with incline loads. Just look at trusses. When we do method of joints analysis, all the loads are at inclines. All the loads are at some angular orientation. So being able to handle this is really, really important. And so this is a good, practice for later. The one thing I want to get across is there's sort of 2 ways to go about splitting up an inclined load. And it just goes to how we spec out civil engineering structures. So if you've ever done any sort of construction, any sort of building, like I'll give you an example. Let's talk about roof pitches. How many construction workers have you ever heard them say that roof is at a 32.6 degree pitch? Or do they say that's a 3 to 12 or 4 to 12 or 5 to 12? I mean, the angles are somewhat common, but what's most in common is just the slope ratio, the rise over run. I think that everybody would agree that's probably the most common way. It's also the most common way that they would be dimensioned on drafting sheets, because if you're laying out, let's just say, a truss, you're just going to lay out all of the dimensions and when you're orienting that truss. One of the things that I've always found maybe mildly entertaining is sometimes we'll have a situation like this. Let's take this one up here. I'll use my little handy dandy pen. Okay. So for example, let's put some numbers here. I'm a numbers guy, so let's put some numbers here. Let's say that you have, I don't know, a 75 kip load, and that's at a 3 to 4 slope ratio. Okay. Now what I have found kind of funny is, okay, it's a 3 to 4 slope ratio. So I have seen students say, okay, I need to use the inverse tangent to compute the angle, and then I need to take sine and cosine of that angle to figure out the x and y components, right? I've seen a lot of students do that. But to me, I'm kind of lazy. I like to do it the simplest way possible. And so if this is a 3, 4, what's the hypotenuse of that triangle? 5. So why not say that the vertical component is 4/5 of 75, and this is 3/5 of 75. Okay? And if you're thinking, well, is that trig? Yeah, it's trig. Do you remember this old mnemonic SOHCAHTOA, right? What is the sine? It's the opposite over the hypotenuse, right? So, isn't that what we got going on right here? Number divided by 5, which is a hypotenuse, or adjacent over hypotenuse. It's a lot easier than trying to figure out some angle. Now, let me be clear. If you're more comfortable doing some inverse tangent to determine the angle and then take sines and cosines respectively, that's fine. I just think it's more keystrokes. It's more scratches on the paper. And I think it just takes a little longer. And to me, my experience has been the more steps that you introduce into a problem, the more potential sources of error that arise. And so I'm all about keeping it simple. Now, to be clear, if you are expressing it as an angle, you might say, okay, if it's, the load is inclined at 22 degrees, yeah, okay, take sine and cosine. But if it's spec'd out by a slope ratio, I would just use the slope ratios directly. One of the other things that happens when you try and compute the angle is you end up throwing in a bunch of rounding. So if you, let's say a 3, 4, 5, if you use inverse tangent to try and find that angle and then you take sine and cosine and you don't track your decimals exactly, it won't come out 3/5 and 4/5. Instead of 3/5, which is 0.6, it might come out 0.61 or 0.59 when the actual answer is just 0.6. Okay, does that make sense? I'm just keep it simple. Don't give yourself more work than is necessary. One final thing. So this slide has sort of the formulas expressed for you. So let's take a look at this bottom scenario. So if you have a load that is inclined at some degree theta, some angle theta, then the x component is the load times the cosine of that angle, and the y component is the load times the sine of that angle. But be real careful when doing that, because in order for this formula to work, the angle has to be referenced from the x-axis. So if for some reason the angle was referenced from the y-axis, if instead you were given, I don't know, this angle, then you'd have to flip. Your sines and cosines would have to flip. Okay, that's just bringing back all that trig know-how from 10th grade or Math 132 whenever you took it. So, sound good? Okay. So let's look at a reactions example. So, and you can see I've got the 3, 4, 5 here. I'm sort of cheating a little bit because we already looked at this. But I have a beam that is similar to the one that we did last time. The only difference is now I have a concentrated load at an incline. So what we're going to have to do is split that load up into X and Y components. Now I think one of the things about this problem that I like in terms of your education is that it reinforces the necessity to identify all of the potential support reactions. Because in the last two problems that we had, as well as your homework assignment that you just submitted that was due this morning, all of the loads were vertical, so the horizontal reactions were 0, you know. But that's not going to be the case here because we have an inclined load. So what we're going to need to do is take this problem and we're going to need to actually determine all three of those reactions. Now I'm going to pull up the notebook. I already have this drawn out, so I promise I won't move away from stuff that you need to see. I don't want to keep my ink annotations. So here's the problem here, and I don't know if that's coming out a little better. Let me know. It seems like I'm looking here on my screen and all the lines look very clear and all the text looks really bold, and then I'm looking here on this television and some of these slope ratios look kind of faded. So if there's something that you can't see, let me know. If I need to redo some of the images, let me know. But I'll give everybody a sec because it looks like you all are sort of copying this stuff down. All right. Everybody good? Okay. So let's start off by dealing with this inclined load. Now, this triangle here, we just looked at this, is a 3, 4, 5. Okay. So what I can do is I can take this 20 kip load and I can sort of turn it into an X and Y component. So basically that's what I'm doing with inclined loads, is I'm just taking any inclined load and splitting it up into X and Y components. And I'm doing that before we go through the process of writing equations of equilibrium. I just think it's easier to kind of split this stuff up beforehand instead of trying to do it while you're also trying to sum equations. I just think that's too much headache. So what we're going to do is we're going to take 20 kips here, and the way I like to think about this, so we're taking this and we're splitting it into X and Y components. So we're using sines and cosines, okay? And if you remember from SOHCAHTOA, sines and cosines are both, you know, either opposite over hypotenuse or adjacent over hypotenuse. The hypotenuse is always on the bottom, okay? So this is going to be 20 kips times something over 5. And this one over here is going to be 20 kips times something over 5. And as for the something, just match the direction. So if you look at your slope ratio here, the 3 is on the x-axis, the 4 is on the y-axis. So put the 3 with the x component and the 4 with the y component. Again, just keep it simple, you know. All right. Now we're not done yet in terms of simplifying our loads because we have this distributed load. So I'm going to turn that into a concentrated load that has a magnitude of what? 14 kips. And how far is that from A? 5 feet. And I think that's enough. I think by now, I think we kind of figure out, you know, how we're going to handle that from an equilibrium standpoint. Now, in terms of our reactions, we've got a vertical reaction here. We'll call that AY. And a vertical reaction here, call it BY. Is that it? No, we have a horizontal reaction at A, AX. Somebody help me out. Which way do you think I should draw it, left or right? To the left. You're pointing that way. You're exactly right. All right. I think I find that when doing a lot of these problems, this is half the battle, maybe even a little more than half the battle. If you can take the problem and simplify this, remember we have a name for this image here, we call it a free body diagram. Y'all remember that? That's kind of what we're doing here, is we're taking this structure and we're breaking it down into its constitutive components, loads and then locations. Once you figure this out, the rest is kind of grunt work. It's pretty straightforward, okay? So remember, we have our three equations of equilibrium: sum of forces in the x direction, sum of forces in the y direction, sum of moments. Okay? So, you tell me, which one do you want to do first? I'm going to let you all drive the train a little bit on this one. Sum of moments. And you specifically identified sum of moments about point A. A sound strategy, because we have two of our unknowns intersecting through A, and then summing moments at A would isolate this reaction at B. Does anybody know of another place, just before we start chugging this out, where's another place that we could conceivably sum moments that would isolate two unknowns?
18 foot from point A, but I don't know what you would consider that.
Well, what I'm getting at is, could we sum moments at B?
Yeah.
Because we would have this reaction and this reaction, right? Remember, there's this principle in statics, it's called the principle of transmissibility, that says that action from a moment perspective acts along that line, and you can sort of move it, forever along that line of action, right? It's like tug of war, right? If you and I are playing tug of war and you're here and I'm here, right? And we're yanking. Of course, I'm going to win. I know I'm a physically intimidating guy, but from a tug of war perspective, it doesn't matter really if you and I are right here or you and I are on opposite ends of the room. You're yanking this much, I'm yanking this much. It's the same scenario, so I can move that in either direction. I could sum moments at B to isolate or to eliminate. I said isolate, I meant eliminate this BY and that AX. Does that make sense? So that would solve for AY. Is that everybody good? Okay. All right. Okay, so I'm going to chug down here a little bit. So we're going to sum moments at A. Okay. And remember, it's just like a checklist. We just start at the left, work our way over. So we're summing moments today because we don't want to deal with AX and AY, so we don't have to worry about those. Starting at the left, working our way over. Boom, we got this 14 kips. 14 kips times a moment arm of 5 feet. Does it belong on the left side of the table or the right side of the table? Left. So 14 times 5. All right. Now we got this incline load. What about this one? This part right here, this horizontal component. Do we consider that? No, because we assume that's acting directly through A. So this one, I know I'm sort of drawing it like up here, but that's just my art skills. The idea is that acts directly through A, so we don't consider that 20 kips. Now, here's the other thing. I'm drawing the beams with some depth, like you can see them as a rectangle, and I'm doing that just kind of from an artistic perspective so you can kind of see that is the beam. But from an analysis perspective, we're basically considering the beam to just be a line. So you can assume that this component here and this point here are collinear. So we don't have to consider the 20 kips times the 3/5, but the 20 kips times the 4/5, you better believe we do need to consider that. So 20 kips times 4/5, what's our moment arm going to be? How far is that from A? 18 feet. And left side or right side? Left. Okay. So 20 kips times 4/5. And then that is 18. Let me cheat a little bit here. Move that over here a little bit. All right. So 20 kips times 4/5 times 18 feet, and that took care of everything except for BY. And BY is going to rotate in the opposite direction at a moment arm of 24 feet. And again, if there's something that's illegible, let me know. All right. So 14 times 5 is 70. All right, we got 20 times 18 is 360. 360 times 4/5. what is that, 288? And just so you know, I'm doing this little multiplication here on the side because we're just getting started. As we start moving forward throughout the semester, I'm going to sort of skip that stuff because I'm assuming you all can do the basic math at that point. So 70 plus 288 is 358. Foot kips equals BY times 24. And so what does BY end up equaling? So positive 14.92. I said 2, not 2. Do I have a second on that?
Yep.
All right, and so that's 14.92 kips going up. There you go. All right. And by the way, if we're talking about rounding, I had a question in here about, or not in here, but in statics about significant figures. I'm going to be honest, I've never really been so worked up about significant figures. There's a meme on the internet about math as a function of education, and it's like for engineers. And so it starts off, arithmetic, algebra, geometry, trig, calculus, differential equations, Microsoft Excel. And it's a joke, but there's actually some truth to it that by the time you get out of here, to be honest with ourselves, you're going to be using Excel or some sort of software package, and it's just going to track the values for you. So from an analysis standpoint, like we're talking about loads, that's 14,000 pounds. You know what I mean? 14,920 pounds. So on kips, if you're a couple decimal places, that's good enough. Okay? That I promise. And when you start getting into steel design and reinforced concrete design, you start to understand the conservatism that's built into the designs. So that's good enough. So, all right. So now we've got that. So let me. What's that? Did I miss something? Did I get something wrong or? Oh, okay. If you got a question, please don't hesitate. I told statics the same thing I'll tell you. Whether it's a scholarship, loan, your parents, somebody's putting cash money on the table for y'all to be here, so get your money's worth. Okay, so now we'll go ahead and do sum of forces in the y direction since we're doing vertical reactions already. So we'll just, everything going up on the left, everything going down on the right. So going up, I got AY and BY, but we already know what BY is, so AY. And then going down, I've got 14 kips. And then I've got 20 kips times 4/5. Which I'm not a format guy. If you wanted to go ahead and put 16, that's fine. So, all right. So, hold on. So AY plus 14.92 kips is 30. And that's positive, what is that? 15 something? 15.08. $15.08 kips going up. Boom. Are we done? No, that's right. We are not done. I saw a couple people shaking your heads. Yes. It's like if you say you're done, take your hand out, do that. No. We got 3 equations of equilibrium. We got sum forces in the x direction. So we'll put everything going to the left on the left, everything going to the right on the right. So I got AX going to the left. And then on the right, I don't have to consider this or this or this or this, but that right there, 20 kips times 3/5, you better believe it, we got to consider that. And 20 kips times 3/5 is what, 12? So therefore, AX is positive 12 kips, which is 12 kips to the left, because that's the direction that we assumed, and we're getting a positive answer. So what's the answer to this problem? I'll zoom down here a little bit. So AX is 12 kips to the left. AY, 15.08 kips up. BY, 14.92 kips up. And that's what I want to see on your reaction answers, is a value and a direction. Remember, these reactions are forces. We'll break it back to statics. Forces in statics we represent as vectors, right? Remember, vectors are mathematical objects that have two components, a magnitude and what? A direction. So that's why when I have AY, I have a magnitude, 15.08 kips, and a direction, up, all right? So that's kind of what I want to see. Because if we're talking about the sign convention, like whether it's positive or negative or whatnot, that positive and negative sign convention is just a function of what you assumed at the beginning. You assumed upwards, and it was upward. What matters is what it actually is. This, by denoting it this way, this eliminates any misconceptions about what your sign convention is versus mine. And let's be clear, okay? I don't think there's any misconceptions over just a beam with some loads on it. What are the reactions going up? I get that. But later on, we're going to start doing problems where we've got some funkier stuff going on. You know, we're going to have trusses subjected to moving loads, and then we're going to have overhanging beams where the moment and the shear changes directions and whatnot. And so having a clear understanding of your sign convention is pretty important later on. So that's why I want you to get into that habit of making sure that you're clear in the expression of the results, the answer and the direction, so that I don't care who looks at it. I got a buddy, Jerry Elkins. He's a bridge engineer at HNTB. If I can take his your homework assignment and give it to Jerry, I want Jerry to know what's going on without any of us having to explain it to him. That's sort of the idea. So, make sense? All right. Okay. Now I'm going to take this problem. Well, first off, hold on. Any other questions about the problem? Okay. Now I'm going to take this problem. I'm going to make it a little more complicated. This is an inclined load. What about an inclined support? Okay. So what about an inclined roller? Okay. Let's talk about this. So an inclined roller, let's be clear about something. An inclined roller only has one reaction, okay? It's just in the direction of the incline. Now I can take this and I can split it up into x and y components, but they're going to be dependent upon one another. The x component is going to be the magnitude times some ratio, or times some trig ratio, and then for the y component, it's going to be the magnitude times some trig ratio. But there's really only one true unknown, just one unknown variable, the magnitude. Okay. Now here's what gets a little weird. Okay. You might remember this up here. Remember this, right? So what this is an old formula that you probably learned in, I don't know, algebra or geometry, some high school class. You might have covered it in 132 or 127, something like that here. But if you have some line, right, and you want to determine what is the slope of the line perpendicular to the line in question, you flip the fraction, right? Now you're changing the sign, the positive to negative, because if you have a line with a positive slope, the perpendicular line has a negative slope, and vice versa. The sign convention, the positive to negative, I'm really not all that concerned about that right here, because when we draw the free body diagram, we're sort of taking care of the sign convention by identifying which forces are acting up and which forces are acting downward. So we're handling that. But I do want to consider that flipping of the slope ratio. So if you have a line that has a slope of 2/3, the perpendicular line has a slope of 3/2, just, flipped, right? So the example that I like to use is, I want to show you, and I have a diagram here that has something you can copy down. But let's take a look at a roller that has a really, really, really shallow incline. Let's talk about a roller. Oh, I drew that backwards. Let's draw a roller that has a slope ratio of like 1 to 12. Okay? So it's barely sloped. Okay? So here's the ground, and let's say the slope is like that, right? So it's just barely up, right? Okay? Well, what's the reaction going to look like? The reaction is going to be perpendicular to this, right? Right? Now, if I split this up into x and y components, I'm going to have a real big y component here and a real tiny x component, right? Because they're flipped. And so what I mean by flipped, when I'm drawing the slope ratio for this, it's going to be like that, 12 to 1, right? So see what I'm doing with the flipping? I have the 12 on the x-axis. Now I have the 12 on the y-axis. I have the 1 on the y-axis. Now I have the 1 on the x-axis. It's just flipping it, okay? Does that make sense? So if I look at, let's say, this image here, this is another special triangle, right? 3, 4, 5, 5, 12, 13. That's another special triangle, okay? All right, so if I have 5 corresponded with the y-axis, when I look at the reactions, now I have the 5 corresponded with the x-axis. The 12 on the x, now the 12's on the y. Does that make sense? That's what I mean by the whole flipping, okay? So you gotta think about that, okay? Everybody okay with that? Don't worry, we got an example doing it. I'm not going to say, oh, just figure it out. We'll see you on Wednesday. No. You don't learn this stuff until you do it. Everybody good? So let's look at this problem. Now, I went ahead and was a little different here. I did an angle. I'd have a roller that's inclined at an angle of 20 degrees. And I also decided to make the problem just a little bit more interesting because, look, I got a triangular load on here just because, okay? Now, again, that doesn't really matter, okay? Because ultimately, I'm going to be able to take that triangular load, turn it into a point load, and actually it makes that problem a little simpler than some of the problems I've been doing before. It's just one load, right? Whereas, I mean, look at the last problem we did. It had, you know, concentrated load, it had distributed load, it had incline loads. It's just one load. Just what makes this one a little weird is the reaction. So let me pull up the notebook again. It's got the same stuff here, so I keep using the wrong keyboard. I don't want to keep the ink annotations. So there we go. Make that a little bigger. I'll give everybody a sec to copy that down. What, this? Yeah. No, that's a good question. This is 20 degrees. That's inclined. I got to say, that's the kind of stuff that I'm happy we're back in person. I got to say, just being able to ask those questions, you know, because in Teams land or Zoom land, you have to type all that out, and I've already moved ahead and started calculations, and yeah, I'm happy to be back in person. What's that? Well, it's like I thought we were friends. Okay. Okay. Let me start off with this angle here. Let's start messing. Actually, no. Let's deal with what we know already. So let's review. Okay. I have a triangular load that extends over a length of 36 feet and linearly increases from 0 to 4 kips per foot. So if I were to collapse that into a single point load, what would the magnitude of that point load be? Let's deal with that first. 48? I'm getting 72. So 36 times 4 divided by 2. I think you might have divided by 2. Yeah. Well, we're getting to that, yeah. So 72 kips, and then now where do I place that load? How far from A do I place that load? 12 feet. There we go. Okay, so I'm going to collapse that into 72 kips, and that's 12 feet. Okay, now let's go away. Let's take a look at this 20 degrees, and I'm going to show you how I'm going to handle this 20 degrees. Okay, so let's look over here. I'm going to draw a really big triangle, 20 degrees. Actually, hold on. I said I'm going to draw a really big triangle, but I'm going to make that a little smaller. Okay, now I have the angle measured from the horizontal. So let's just look right here. Okay, now if I look at this triangle, right, and if you remember, if you have a triangle and the hypotenuse has a length of 1, then the cosine is the length of this leg and the sine is the length of this leg. So what is the cosine of 20 degrees? Somebody give me that in, we'll say, 3 decimal places. Wait, what'd you say?
0.939. Am I doing something wrong?
94. Okay, I'm sorry. No, you were right. I can't read my own handwriting because I thought I had 970 and it's 940. You did everything right. I got that one wrong. So that's a small mistake for me. I'm allowed 7 mistakes per semester, but we're only going to count that one as a tenth of a mistake. It's a corrupt system because I'm the one who's tracking the mistakes too. So I've never gotten to 7 mistakes. Never. It's crazy, I know. Okay. Sine of 20 degrees is what? 3. What was that? Okay, did I write that one down? Yes, I got that one right. 0.342. Okay, so here's what I'm going to do. Okay, all right. Now the reaction. So this is a roller. There is only one reaction that goes like this. Okay, and we're going to call that just RB, just the reaction at B. Okay, but what I'm going to do is I'm going to take this and I'm going to split it into X and Y components, but the X component is going to be 0.342 RB. This is going to be 0.940 RB. So again, I flip, right? This 940 was on the horizontal line. Now I'm putting it on the vertical component. This was on the vertical. Now I put it on the horizontal. Does that make sense? And it's because it's perpendicular, right? If you have the roller, the reaction is 90 degrees, perpendicular. So far, so good? All right, now, don't forget the hinge. It has a Y, and there's also an AX, right? Now, here's what's also kind of wild is, let me ask you this. Is this 0? No, it's not, because here's the thing. There's no horizontal load. But because this is at an angle, it's going to have a horizontal component, so that's got to resist it, right? Again, this is one of the reasons why I kind of like this lecture, is because it forces you to be consistent. It forces you to go through the bookkeeping. It forces you to handle it, to handle each component, all right? And again, 3 equations. 3 unknowns. Now, I want to clarify something before we start checking out some numbers. We're going to do this problem the same way we did the last one, right? We're going to sum moments at A to determine the reaction at B, and etc. But to be clear, if you sum moments at B, these are not 2 unknowns, okay? There's only one unknown here, which is RB. You're just taking RB and splitting it up into X and Y components. So, I don't want you to think, oh, I can sum moments here and that eliminates these two unknowns. So they're not two unknowns, it's just one, okay? So if you sum moments here, you want to make sure another independent unknown goes through this. So like AX, okay? So you can still do that, but that's just something to keep in mind. Everybody good? All right. So we're going to sum moments at A. All right, so let me do this down here. So if I sum moments at A, I don't have to consider AX, don't have to consider AY. I got 72 times 12. All right. Now what about this reaction? Now the RB, I don't need to handle the RB because I can split the RB up into X and Y components. The X component, do I need to deal with that? But the Y component I do. The Y component is on the other side at a moment arm of 36 feet. So we can say 0.940 RB, 36 feet. Okay. Let's see. So we've got 72 times 12. And we've got RB times that. And so this one I can't do in my head. So what do we got? Say it again. 25.53. Do I have a second on that? What? I did something wrong, but I caught it. What did I do wrong? That's what I did wrong. What did I solve for? I solved for RB. RB is not pointing up. RB is pointing that way. So really what it should be is that. Yes, sir?
You really have your heart set on us converting it from like cosine of 20 degrees to the decimal?
You could leave it cosine. That's fine. That's fine. For me, it was just easier for me to show the numbers and where they went. I'm not a micromanager. You can do it however you want. If you want to leave it cosine, that's fine too. I'm serious. I'm totally fine with that. That's a great question. Sound good? All right, which one you want me to do? Sum of forces in the Y or sum of forces in the X? Doesn't matter. Let me pick one.
Y.
Y. So, if I go up here, the only thing I have going down is 72 kips. And as for what's going up, I have AY and I have 0.940 RB. So, what I'll do, I keep scrolling up and down. I want to try and avoid that as much as I can. So somebody tell me what AY is. Say it again. 38.16. I'm getting a little bit of a different answer. See, I got 48 even. Well, what's RB? 25.53. So 0.94 times. Yeah, you can't forget that. Yeah. That's a great point. The slope ratio is still there. So it's 72, it's not 72 minus RB, it's 72 minus 0.94 times RB, or cosine 20 degrees times RB. So 48, do we got that? All right. Now, when we do sum of forces in the x direction, I am going to have to scroll a little bit. So when we do sum of forces in the x direction, all I'm going to have is that and that in equal and opposite directions. So if I sum forces in the x direction, all right, so what do I got? I've got 0.342 RB and AX. And so we know what RB is. What is AX?
8.73.
8.73. Do I have a second on that?
Yeah.
All right. So 8.73 kips to the right. I think on mine I got 8.74, but I might have been tracking decimals a little differently. That's fine. All right, so there you go. So that's going to the right. That, and then RB, sorry, 53. I'm going to show you something on the homework before we leave. But any questions? All right, give me 1 second. All right, so here's your homework assignment. So I'll show you 2 problems. The first problem, I took a problem that was in the textbook and I edited it a bit because the problem in the textbook had a concentrated moment. I took that off because we haven't talked about that yet. So I didn't want to, again, I don't want to be one of those professors that like, here's what we do in class, now here's your homework assignment, and it's completely different. I want to make sure that we're following along. Now, the problem the second problem I just wanted to show you just so that you're clear, this is the second problem. This is a hinge support, so this is, the triangle. That's the roller, okay? This is from a different textbook. I really like this problem, though. There's actually a couple of ways to go about this problem. I don't expect you to do this on the homework, but just to show you, if you wanted, you could sum moments there, right? Where this reaction and this horizontal reaction intersect. You know what I mean? You could do that. I'm not saying you have to, but you could. If you really wanted to get crazy, you could sum moments there, where those 2 reactions intersect. Again, you don't have to do that. I just want to show you that. So the thing is, the structure doesn't care how you do the math. The answer is the answer. You know what I mean? So yeah. All right, any other questions? That's all I got, everybody. I will see you all on Wednesday.